Monroe. I'm on the faculty in the Department of Physics here, and also a member of the Joint Quantum Institute, which is something rather unique in academics and government laboratories. We are joint between the university and the National Institute of Standards and Technology. This will be, since we are in such an intimate setting, please interrupt me anytime with questions or comments. So my job today is to basically teach you quantum mechanics, and if that sounds ridiculous, it's not, because quantum mechanics is really easy. The concepts, you can write them down, they're quite simple. The mathematics behind solving certain problems can be very hard, but that's true in all of nature. I mean, to calculate the mathematics of the weather is really complicated, but we sort of understand when a front comes in, we're going to have rain or something like that. So the main points of quantum mechanics are very easy to digest, easy to understand what they mean. And so that's sort of how I like to teach quantum mechanics, and certainly how this lecture is going to go. Well, this is a rather bold title, because the thesis is that quantum mechanics will actually dictate the future of all computing at some point. Not yet, maybe not even in 10 years, but certainly in the next several decades, and by the end of the century. Why is that? Well, it has to do with what computers are. Computers are always made of some physical device. This is just one example from a long time ago. The first digital computer in the US, called ENIAC, was made of these vacuum tubes. We don't see these much around anymore, but these behaved as perfectly fine memory elements. They broke a lot. They weren't the best type of technology. Come on in, if you want. If anybody wants to, come on. And what happened shortly after this ENIAC computer was the development of solid-state electronics, and this is actually the first solid-state transistor. It doesn't look so nice and miniaturized. And this is sort of where, I would say, where my laboratory is right now in terms of using quantum mechanics for computing. But the neat thing about this is that it was made out of this chunk of solid. In this case, it was germanium. And because it's solid, come on in. Please, have a seat. Plenty of room if you'd like to.
We're just looking around, seeing my old classroom.
Okay, you can even leave before I'm done if you want. No problem. You might like it. If you've never seen an individual atom with your own eyes, you'll see it live. Yeah, you'll see it live here. We're going to have a link to the laboratory. So many of you know what Moore's law is. Maybe you don't know the definition of Moore's law, but you certainly know that computers over the last few decades have gotten unbelievably powerful, mainly because these transistors, these individual elements have gotten really tiny, so they can pack lots and lots of them on a chip. And Moore's law is simply that the number of transistors that have been packed on the chip over the years has grown exponentially. This is a funny plot. It's called a log plot. It's a factor of 10 every division here, and you can see this is roughly a straight line. Every couple of years, the transistors get half as big, and you can pack twice as many. And so the reason Moore's law interests physicists right now is that this line cannot continue forever. And the reason is chips are always the same size. You can't make a chip really big, because then the wiring, the communication lags and so forth is really a problem. The chips have always been the same size. If you ever looked inside a computer, the chips haven't really gotten smaller. We've just been packing more and more in. And given that, if we keep along this line, in about 10 years or 20 years, each little transistor will be about the size of a molecule. Come on in, have a seat.
Okay, sure. I apologize for being
no problem. So each transistor will be one molecule. Well, a molecule is a pretty complex form of matter already. It has lots of atoms. So wait a few more years, and then each transistor will be an atom. At that point, we really have to stop, because to break an atom apart takes too much energy. We're not going to have a nuclear reactor on each of our computers. So
you do that with neutrinos, right? Putting neutrinos and shooting them to the center of the atom, right?
Neutrinos, oh, they're all over the place. Yeah, the problem is they don't interact with anything. You can't really use them. You can't look at them. You can't see them. So we need our transistors to be made out of normal matter that interacts with electric fields, it interacts with our fingers, we can touch it, things like that. We can do electricity on them. Okay. So at some point this is going to stop, and as soon as this law stops, computers will stop getting better. That's a big problem, economically and so forth. Well, just like the last 50 years, the laws of physics sort of dictated what type of computer we can make. We are now at the verge of having to confront quantum mechanics, because when you get down to the individual atom and molecule memory elements, quantum mechanics are the new laws of physics that you have to deal with. And I love this line of Richard Feynman. You may know him. He's a very colorful physicist. He's written many popular books. They're quite readable.
He saw the Challenger explosion, didn't he?
Pardon me?
Richard Feynman saw the Challenger explosion.
Oh, he was one of the panelists that commented and researched what happened, and he was rather outspoken in his views on things. That's the way he is. And actually, this quote sort of attests to that. This is a long time ago, shortly after this first transistor was developed, and he said, "Well, let's think about when we make it really small." And he's thinking 50 years in advance here. And he says, when we get down to individual atoms, things will be totally different because there are new laws of physics involved. You guys want to come into a lecture? That's all right.
Transistors have a collector, base, and emitter to them, don't they?
They do. Indeed they do. There's lots of ways to do computing. Well, what Feynman says, when you get down to the level of individual atoms, there are new laws of physics that take hold. And he thought maybe there would be new opportunities for design. He didn't know what he was talking about back then. In fact, I would say we only are now starting to discover what he was referring to. It turns out when you use quantum mechanics in its full glory, there are ways to continue along Moore's law and make devices much more powerful. So I want to talk a little bit about that before this before this gets a little more fun. Let's get into the rules of quantum mechanics. I promised you I would teach you quantum mechanics. Well, quantum mechanics, you've probably heard about it. It's this weird esoteric law of nature discovered about 100 years ago in the early 20th century, and it was largely a curiosity. Even in physics, it was kind of a curiosity. It never really played a big role in much outside of how superconductors work. And again, how often do you come across a superconductor? Outside of Maryland Day out in front, you saw one probably just this afternoon. But you don't normally see these things. Superconductors are fairly exotic. You don't usually get to such low temperatures near absolute zero.
Technology, right?
Sorry?
It's called zero-point technology, a superconductor.
No, I wouldn't call it that. It's based on quantum physics. It's very complicated.
Does it stop electrical resistance from happening?
Well, maybe we can talk about it later. We can talk about that subject later. Basically, because I don't understand it. Whenever you hear somebody say that, we'll talk about it later. It means the speaker doesn't know what he's saying. Superconductors are incredibly complicated, it turns out. But they may turn out to be the backbone of a new electric grid.
You get the full power of a superconductor, don't you?
Maybe afterward we can talk, okay? Instead of interrupting all the time, okay?
Yeah.
All right, no problem. We can talk right after that. I'd be happy to entertain any questions, okay? But I have a limited time here. So you've all have heard of these luminaries, Al Einstein, Erwin Schrödinger, Werner Heisenberg, Niels Bohr, and so forth. They put together this theory that had to describe matter at very basic levels, but because we're big, because we're made of 10 to the 27 atoms, we don't typically see those laws manifest in nature. Until now, we're starting to confront this in the laboratory, and we're starting to see that we can maybe make new devices based on these laws. All right, what are the laws? I promised you I'd teach you quantum mechanics. Here they are. Quantum mechanics only has 2 rules, and they're very simple. I can discuss them with very little math. The first rule is that quantum objects, anything that's quantum, can be described as a wave. And it sounds a little vague, but waves are interesting and nice to think about because we all know waves, sound waves, water waves, we've all dealt with them. Well, quantum objects are also waves. I'm actually a wave. Fundamentally, I'm a quantum thing, even though it's very complicated. I have 10 to the 27 atoms. But when you take one atom, it becomes easy to describe this wave. And a wave can be in what we call a superposition. A wave can be in multiple states at the same time. Come on in if you want. Come on in if you want. Anybody? All right. It's nice. Used car sales. Okay, so we tend to think of quantum systems as being able to do multiple things at the same time. Like this coffee cup, in principle, can be in 2 places at the same time. Quantum mechanics allows this. And that is a little strange. On the other hand, when you throw a rock into the pond, it sets off a series of circular waves. Those waves are everywhere at the same time.
Yeah, probably.
Right? When you hear two notes on the piano played together, those are two sound waves. They're both there. So in a sense, the idea of superposition is not such a big deal. What is a big deal is there's a second rule here. And that sort of makes everything safe, and it's also bizarre. The second rule says that these waves, and they can be in multiple places at the same time, that's fine, as long as you don't look. As soon as you look, as soon as you observe one of these funny states of quantum waviness, it randomly collapses into one or the other state. Okay? Now, I'm not really covering anything up. These are the two rules of quantum mechanics. This first rule on waves can get really mathematical, but it's very straightforward. It's like describing how water waves on the beach crash into the shore. That's super complicated. Or like I said before, the weather, how a hurricane develops. Super complicated. We can't really do these things on a real calculator, on a real computer. And quantum waves are like that too. They can interact in very complicated ways, but it's very straightforward, the mathematics. We understand how that mathematics works. What's ridiculous in quantum mechanics is this second rule. Because this second rule says that something happens just because we looked at it. And you should be unhappy with that. There's no other theory in nature that has that. That has a special place for the observer. And furthermore, there's no theory of nature that has randomness inherent in the theory. And so rule number 2 says you can't look at it if you want to have both, say, two states, 0 and 1. But when you do look, there's randomness that pops into one or the other. Okay? And that's it. These are the two rules of quantum mechanics. And it is impossible, as far as I know, to derive one from the other. These are two totally separate rules, and there they are. That's quantum mechanics.
The quantum computers both on and off at the same time.
That's right. That's right. You can consider 0 and 1. I call it a qubit. It's a new way of storing data. Instead of zeros or ones, we can have one device that stores 0 and 1 at the same time. So maybe you can use your imagination to see how you might use that for computing. Well, much of 20th century quantum physics was concerned with rule number 1, calculating little effects at low temperatures, little corrections to the known laws of physics. But it's this rule number 2 that is starting to take over the community. And here at University of Maryland, this is the new building that will open this fall. Housed in the basement of this building is the Joint Quantum Institute. We're, by most accounts, the biggest group in the world that's investigating these strange quantum properties and putting them to use in certain applications. So as you come to Maryland Day, year in, year out, you'll see more and more of this. Okay, so now I want to dive a little bit in how would you wire together quantum systems like this, and I'll give you some examples. Now, I mentioned sound waves. Sound waves are used to them being in parallel. We can hear multiple sounds at the same time. Sound is actually really complicated, and if you looked at the exact pattern of a sound wave, or if you measured how your eardrum moves as you listen to a Beethoven symphony or something, it's extremely complicated. Even if you write music down, you can make it arbitrarily complicated, and there's superpositions of many notes here. Now, this doesn't look like it sounds very nice. I'm almost certain it doesn't. But the way we perceive sound, we somehow make sense of all these different pitches. And I want to play for you a little example of what might be called an auditory illusion. And this is a wave file up here. I can expand it. This is the x-axis here is time. And you can't see the right side over there for some reason. Let's see if I zoom. Doesn't want to do that. I guess we can't do that. Well, this takes about 20 seconds, and if you look in here, it's a very complicated sound wave, and your eardrum will basically follow that path. It actually sounds pretty neat. This is a neat sound. Now, on the bottom screen is something a little different. These are like all the notes that are being played. Picture this as a piano. High notes, low notes. This is from 20 hertz to 20 kilohertz. That's pretty much what we can hear. And we have many different sounds going at the same time. You can clearly hear that they're descending in pitch continuously. But it never seems to end, does it? go back and you hear a higher pitch again, everybody's going to hear that transition in a different way. What's happening is there are many notes in superposition. You're hearing them all and you're grabbing onto maybe just one. And as the note gets lower, its volume goes down. And at some point you lose the ability to hear it and you jump onto something else and you follow it down. Now this is not a quantum superposition, but it's a little like this law of quantum mechanics I said. We have a superposition of notes and you've made a measurement. You pick one of them out and then it dies away and you have to make another measurement. So the observer, different listeners will hear those sounds differently. There are lots of different examples that are like that. But it has to do with the wave nature of these sounds. You can hear them all at the same time. Okay, so I like to teach with using analogies, and that's one of my favorite ones. There are many others in music, but let me see if we minimize this. So let's go back to the to quantum mechanics and using them to compute. So there's one little detail in this quantum superposition that gets really weird. It comes from those two rules, and the fact is we can hold on to superpositions of not just a qubit 0 and 1. We can also make a superposition of multiple qubits. So imagine I have two of them. They can be 0 and 1 at the same time, and somehow I make a superposition of both 0 and both 1. This is a very weird quantum state because the blue one and the red one can be really far apart from each other. One could be on Jupiter and the other could be on the Earth. Yet when we measure them, when we observe them, they will always give the same answer. Right? If we have two of these, I think of coins, quantum coins, say. They're both tails and they're both heads at the same time. And I have my coin, you have your coin, and you go to Jupiter. As soon as I look at mine and I see tails, it's totally random. Until I look at it, it's tails. I know at that point that you also have tails. I know something about your coin, even though you didn't tell me. And I know that information faster than the speed of light could make the trip. And there's a trick behind that. It's actually not information because it's just random. You can't use it to send information faster than light. But it's weird enough that Einstein in 1935 famously rebelled against quantum mechanics, saying that's ridiculous. You can't imagine having something that happens instantaneously across the universe. Well, it turns out Einstein was wrong. I think his heart was in the right place because this is just super weird. The ability to have two quantum bits have a communication line even though there's no communication. This thing is called entanglement, and it is actually what we think of using for advanced computation in the future. So let me give you an example of what it would be like to have two entangled coins, a red coin and a blue coin. What it means, we're flipping two coins, and we might be on opposite sides of the universe, but they're always ending up the same value. Individually, come on in if you want. Individually, the coins, please have a seat. Individually, the coins are perfectly random. You can come on in. Oh, come on, it'll be fun. We're going to go, if you've never seen a single atom before, you'll enjoy this. Okay. So the idea is each coin is random. In fact, if you have no idea that you have another coin across the universe, you just see heads and tails at random. But it's perfectly correlated with this other coin. So there's a certain wiring going on here. If these two coins are prepared in that quantum state, they're sort of implicitly connected in this very funny way. And you can keep tabulating this. Now, what is this useful for? Well, it turns out it is useful to have a bunch of random numbers that are perfectly correlated across the globe. You can use that for secret communication, it turns out. It's called a one-time pad. It's a generator of perfectly random numbers that you can use for communication. Now, I want to make another analogy, and this time not music, but visual illusions, optical illusions. Now, you all know that when you draw something, when you draw a three-dimensional object on a blackboard, you have to use perspective. And you can play games on what the perspective is. This cube, come on in if you like. We have a lot of time to go. This cube is drawn with ambiguous perspective because the lines, this is supposed to be like an ice cube. These lines are perfectly parallel, so if you did this with proper perspective, they would kind of come to a point. But this is drawn with ambiguous perspective. You don't know if the front face is this one here, or is it pointing up and to the right. See? That could be the front face, or that could be the front face. So to me, this is a little like a quantum superposition, and in fact, your mind will sort of go back and forth if you want. You sort of see this and that. It's like a qubit. You're seeing both states at the same time. But typically, when you lock onto one perspective, that's like a measurement. It stops. It's random, and then you have to, if you want to do it again, you have to close your eyes and shake your head a little bit and do it again. And you'll see one or the other each time you make a measurement. That's a little like a quantum superposition. And here it states a definite perspective, shaded in accordingly. Now, the neat thing about this analogy is that it works for entanglement as well. And here's how it works. Now, entanglement involves two or more quantum bits, and here they have both ambiguous perspective, but I'll bet you when you look at this, you find that they collapse to the same perspective, both pointing down to the left or both pointing up and to the right. So that's a little like entanglement. Now, it's only an analogy, so it can't be taken really far. In fact, you can mess around with this. If you look really hard and concentrate, you can get the cross terms. It's hard to do that. It's more natural for you to see them the same perspective. And that's something that goes on in your head. I don't quite understand it, but
Einstein called it spooky, didn't he?
He did. See, I quote him right here. Spooky action at a distance. Now, this analogy doesn't really go very far because when you separate these things over a distance, it falls apart. The visual analogy doesn't quite work. These are totally independent now. But quantum mechanically, it does work. Quantum mechanically, they will be entangled. They will stay correlated no matter how far you go. All right, so it's this wiring. It's this inherent wiring between these two qubits that allows us to compute. We don't have to make the wire. It's sort of already there. And that's the trick in quantum computing. Yeah, you have a question?
So is there a limit on, like, if you have two particles, like you introduce them together or something, and is there a limit on, like, how long they stay entangled?
Oh, as far as we know, there's not.
So the particles, they're always going to be
Well, I mean, you bring up a really good point, though. And remember rule number 2. The good stuff only works when you're not looking. Now, if you put a piece, if you put this one coin on Jupiter and leave the other one here on Earth, it's very unlikely that somehow they're going to survive not being looked at. I mean, that's a really big system. You somehow have to bottle it up. And the further apart in practice you make this entangled state, the more likely they will see their own environments. And you don't have to have a conscious being measure it. If one is exposed to air and the other's not, the air can screw things up also. So you bring up a good point. In practice, it's very difficult to make entanglement and harness it. Yeah?
Don't the two things have to initially be together in order to be entangled? And then
In general, they do, but if we use light, if we use photons to entangle, they can actually travel through optical fibers without much loss and so forth. But in general, yeah, they have to somehow have an interaction, and then you want to pull them apart. Very much like these cubes.
Does
Yeah.
string theory help to explain quantum mechanics?
Good one. I don't know anything about string theory.
Help to explain quantum entanglement, string theory.
No, I don't think string theory really. String theory uses quantum mechanics as a foundation, but it doesn't really explain quantum mechanics. Yeah.
I said entanglement. Was it entangled?
No.
Oh, okay, all right.
when you talk about collapsing the way it functions, you say you have two errors, you have their coordinates, does that change something?
No, it doesn't change it at all. We're going to go to the lab real fast. You want to see the atom?
Sorry, video.
Yeah, two observers, they'll later compare their results and they'll show that they're perfectly random and correlated. It's very hard. I mean, you could time, the trick is there's no information transfer, and that's why it doesn't violate any physical laws of it. And Einstein really didn't understand in 1935 what information was. He was very, at the time, there was no mathematical theory of information. So that made it seem like a paradox. Okay, so we want to use this entanglement to wire together a quantum system and make a new computer. In this Dilbert cartoon, he's poking fun at one interpretation of quantum mechanics that says the second rule, when it pops into one or the other, what actually happens is the universe splits into two. And we have our own universe where this coffee cup is over here, but there's another universe where the coffee cup ended up over there. Okay? So that's a nice, neat answer to quantum mechanics, but it involves, I think it comes at a huge expense of invoking zillions of universes. So I want to now talk about quantum hardware. I really don't have time to talk about, I mean, I can just flash this slide up there. There are many applications of quantum computers right now that involve some math problems that become very easy if you could wire up atoms with entanglement and so forth. But I really want to get into the laboratory. And of course, if you want to do a physics experiment, you have to consult Tom Clancy. He knows everything about engineering and physics. And here, one of his heroes talks about using a quantum computer to play cards. And he says, well, you hit a trapped atom particle with laser light, and then you begin to bring it back down into your switch. Rows of atomic ions give you smallest, fastest computer on Earth.
That's coherent light, isn't it?
Yes, it is. And this is exactly what we do in the laboratory down the road. We remember rule number 2 states, come on in if you like. Please interrupt us. You're not interrupted. No problem. To obey rule number 2, you have to be able to have a system that's not observed. It has to be isolated. That's very exotic. So in my laboratory, we have, this is a window. It's only about 4 inches. Inside that window is a vacuum. We've pumped out all the air. And if you look closely, there are these gold electrodes. In the middle, there's nothing there. There are electric fields, and they suspend individual atoms in a row. And here you can see about 15 of them. Doesn't matter what kind of atom. Well, it does matter very much what kind they are, but these happen to be ytterbium atoms. And the reason you can see these individual atoms is that we have a microscope here, trained on where they are held. And we also shine laser light in there. Laser light at a very specific color that only the atoms will see. Atoms are very acute. It's very specific on what wavelengths they like to see, and we know what that is. So we tune our laser to about 10 digits of accuracy. We spend most of our time doing stuff like that. And send the laser beam in there, and it scatters light into this lens. See, it's just like the way you're seeing me. You're not seeing me. You're seeing the light bouncing off me. So we're doing the same thing with these atoms. So these individual atoms occupy a very small space. The atoms themselves are much smaller than these blobs, but because due to a funny thing about optics, when you try to look at something really small using light, you're limited in resolution. It's called diffraction. And these are diffraction limited point spots here, and so they're sort of fuzzed out. But there's several of them, and because these atoms are charged, they repel each other. So we form a little very simple crystal.
This is a form of an optical computer, correct?
It's not optical.
Not
It doesn't have to be optical. But speaking of crystal, this is a graduate student in my laboratory. Crystal Senko is her name. We are now going to go over to her in the laboratory. I have a Skype hookup with her, and she can hear me. Give me a thumbs up if you can hear me. Oh yeah. Let me display her on the screen here. Sorry. Be right with you, Crystal. All right. There she is. Except you can see me too. Hold on, Crystal. Let me move this screen over so everybody can see you. Okay. I need to turn on the sound on Skype. Just a second. Let's see, tools. Does anybody know how to do that? Oh, audio settings. Yeah. Okay. Say something, Crystal.
I'm saying something.
Excellent. We can hear you. Okay, Crystal. The crowd here knows a little bit about quantum mechanics. They know the rules. They know that trapped ions are one of the best ways to do quantum mechanics, and maybe you can show them what you're doing.
Yeah, sure. So here is the actual lab where we're doing the experiments that Chris was talking about. I'm going to show you in a second here, as soon as I turn my laser, a collection of atoms like the ones that he's been telling you all about, and show you how we can really see individual atoms in this lab, which is one of the really cool things that we can do here. It's not something you can really do anywhere else. So I'm going to move the camera now. Behind me is the table where all of the action takes place, so I'll give you just a couple seconds overview of that. Over here we have a box, but in there we have a bunch of optics. Down a little bit over there on the corner. And I showed you the atoms, and I might come back and show you the chamber that Chris showed you in his talk video. Okay, so over here are the computers that we use to control our experiments. And here, I'm zooming in on a hammer of 6 individual atoms. So you can see here that I have 1, 2, 3, 4, 5, 6 bright spots. And we can see those individual atoms because they're actually very far apart as atoms go. So this is still a very, very small amount of space. We have a microscope blowing it up quite a lot. So the distance from this guy all the way on the left to this guy all the way on the right is about maybe half the width of one of my hairs. So it's a really small distance. But usually atoms are 1,000 times closer together than that. And so that makes it easier for us to see them when they're in this sort of special trap that we make. And so Chris was telling you that the laser that we use to see these needs to be at a very, very particular color. I'll move the camera up a little bit so you can see the number on the top left of my screen here. That number that says 405.644.327 THz, that's telling you exactly what color the laser is. And if you move it just a little tiny bit, a few digits at the end, then you'll see that the ions actually go dark. You won't be able to see them. So now we're going to move it by just a little tiny bit. It went from 324 at the end to 300, and our ions are completely gone now. You can sort of see them still scattering a little bit, but they're really fussy about what color they want to see.
Anybody have any questions? Crystal, speak up.
Yeah, I can't see anybody. I don't know how they're reacting.
Okay, we have a few questions. So they want to know what the other dots are on the screen.
Most of the other dots are noise. So there is some noise when you compare it to the camera, and then you can see there's sort of a disc here. Yeah, can everybody see that?
Yeah.
So what that is there's some light scattering. The lasers that we use to look at the atoms are just scattering a little bit off of parts of the vacuum chamber and getting into our microscope.
So what's holding the atoms there?
What's holding the atoms there?
What's holding the atoms there is a set of electrodes with voltages on them. So, Chris, do you have the picture of the trap up? Did you show them that?
Yeah, let me show it back real fast. Sorry. Okay, so there's a picture. In fact, this is the exact same trap that Crystal is using now. The same equipment here. And so there are voltages applied to these gold electrodes, and all the action is right in the middle there. It's a little tiny thing. I mean, that looks just like what you saw on the TV camera. So there are electric fields. They're radio frequency and static electric fields that are specifically applied in the right way to form sort of a cigar-shaped well. It's sort of like a bowl in 3 dimensions. It's very tight in 2 dimensions, very loose in 1 dimension, and that's why these things form a linear crystal. If we were to squeeze it in this direction, something else would happen. Maybe crystal will do that in fact. Okay, back to you.
Showing them how the trap looks when it's in the middle of our table. So I don't know if you can see it all from here. Chris, can you tell me if that's...
Yeah, that's good.
So you can see that it's a little bit more crowded than the picture that Chris showed you.
So that's the microscope right
Let's
there.
see if I can do this without dropping the camera. We've got a microscope here. This is a lens that's collecting the light that's going to the camera that we were looking at before. And then this is a lens that lets us focus lasers onto the atoms. So hopefully...
Can you back up maybe so they can see a more overall...
Yeah.
Yeah, that's better. So these big tables here, there are big lasers on there. It's all about the lasers. You keep pointing at lasers. But all the action is in this little vacuum chamber here.
What's the class of the laser that you're using? There's class 1, 2, 3, and 4. Which class are you using?
For what?
For this experiment?
Each class, what?
Laser?
Oh, I don't even know. I should know. If there's any ocean people in the audience, I really do know them.
They're all class 3 and class 4 lasers.
Okay.
She knows way more than I do. Okay.
Mostly class 3 and class 4 lasers. Okay, so we'll go back to the atoms, and somebody was asking how we trap them. We're using the voltages on that electrode that Chris showed you to trap them. You can also change those voltages to move the atoms around. So let's see what that does.
She's going to play with some voltage knobs. Watch the crystal there.
How do you introduce them?
So now I'm going to change one of the voltages on one of the electrodes. Because these are charged atoms, when I increase the voltage, that's going to be pushing on the atoms and moving it away from the thing that I put the voltage on. So let's see. First I'm going to move them to the right side, I think. Right. Kilograms to the A. Kilograms to Z.
bowl here, an electric bowl. Just moving it back and forth.
We can move it around side to side, move it up and down, or position them wherever it is we really need to position them. We can even squeeze them from both sides so we can control that spacing. I was telling you that that distance is like the size of my hair or so. We can make it even smaller than that just by pushing harder to mold this. We can make them make even more interesting shapes of these lines. So that's pretty cool how we can make, you know, from lines to circles to all sorts of different shapes depending on what this one is doing. Do you have any other questions there while we're at it?
Any other questions for Crystal? Yeah, there are a couple. Go ahead.
What would happen if you shut the voltage off completely?
What would happen if you turned the voltage off completely?
If I turned the voltage off completely, they would fall. So they're suspended in the middle of a vacuum chamber.
She won't demonstrate that. She could demonstrate it, but it turns out loading these atoms, I mean, you can see they last for a long time. We've had atoms last for months. The same atoms in the trap for a few months at a time. But in practice, the bigger crystals they only last for hours due to things we don't quite understand. And loading them is a little painful. It might take 10 seconds to an hour to get it loaded just right. So she doesn't want to dump them right now.
How are you loading them?
How are we loading them? They're loaded from, basically we produce, it's a very uncontrolled process, we produce a neutral atomic beam of ytterbium. So we basically sublimate ytterbium by heating up a wire ytterbium. And it goes everywhere, but it's neutral. It goes flying right through the trap. And at the same time, we send a blue laser at just the right wavelength, again to 9 digits. We know this is a different laser. It removes an electron. It's tuned just right, so it removes an electron. And now this atom is all of a sudden charged, and it says, hey, look, I'm in a bowl. And it stays there. So it's not very controlled, but we can pretty much get it right by changing the temperature of the ytterbium and the tuning of the laser and so forth.
How did you know to tune the laser to 9 digits to do the trap? I mean, was a formula told you that, or?
No, not a formula. Previous data for the last 50 years. Atomic spectroscopy.
Yeah.
A lot of it happened at NIST, National Institute of Standards and Technology. They're developing wavelength standards, and it's a fundamental parameter that it's very hard to calculate. I don't think you can, but you can measure it. It's known. It's written down. So we weren't very smart. We just looked it up. There was a question over there. Yeah.
Why did you choose this one?
Why did we choose ytterbium? That's a really good question. Turns out ytterbium is like helium. It has 2 outer electrons. And when we ionize it, when we take one out, it only has 1. And we want atoms that have 1 outer electron only. We could have used calcium, magnesium, beryllium, strontium, barium. Ytterbium is also one of those. So the main thing is it's charged, and we can actually make it. It has all the right. Come on in, have a seat. Are there any more questions for the lab? Yeah, in a sense, this is the world's most perfect solid, atomically perfect. However, it's very small. We like to do this with about 1 million of these atoms. We don't exactly know how to do that yet. Yeah.
So is there like a specific temperature?
Sorry?
Is there like a specific temperature that this situation?
Temperature, you said?
Yeah. Is there a specific temperature that this situation has to be?
Yeah. The vacuum chamber is at room temperature, clearly, because it's just sitting there in the lab. But it's a vacuum, so there's nothing there. So temperature doesn't mean a whole lot if there's no coupling. Now the electrodes are at room temperature, but they're so far away, they're almost a millimeter away. So there's no, it's not like these atoms have to be at room temperature. In fact, the atoms are very cold due to their interaction with the laser. That's called laser cooling. My colleague Bill Phillips won the Nobel Prize for this. He's here at the JQI as well, Joint Quantum Institute. It's a well-known technique to produce small samples of atoms that are super cold. This is a hair above absolute zero. It's maybe a millikelvin, 0.001 degree above absolute zero. Yeah.
You said you would, you're trying to strive to have billions of these. What would be the result of having billions of this reaction happen? What would happen?
You said reaction.
You said like what? You said, I wish we could do this billions of.
Oh, I wish we could.
What?
Yeah. The problem is these atoms are actually pretty far apart. They're microns apart. If you had billions of them, they'd occupy a big reach. It becomes like your question on. They're so far apart, then they see different environments. It's very hard to maintain a quantum system that big.
Okay.
That's not a fundamental principle, but in practice that's the case. And the whole field of quantum computing is trying to build bigger and bigger quantum systems. This is actually the state of the art. Around 20 or so we're able to hold. And that's the biggest quantum system under this amount of control ever. And it's only 20, so we really need, I mean, to make something as powerful as this computer, for certain applications we need a few hundred of them. But for general applications we probably need a few million of them. So it's pretty speculative stuff. All right, any more questions for the lab? Crystal, did you show everything you wanted to show?
Yeah, I think so. Is there anything else you wanted to see?
Yeah, I guess there's not much you can do with these guys except dump them. If you want to do that, go ahead. It's not very exciting. It's so dark.
I'll show you what it looks like when we turn the voltages off. Here's what it looks like. There we go.
So in practice, they stuck to a wall. When we turn the voltages off, they're ions. They'll just sort of get dragged around in any straight electric field.
Do you let the machine run forever? Do you let it run 24 hours a day?
We actually turn the lasers off at night usually, and we don't typically dump the atoms. Oh, wait a minute.
I cheated. I turned off the laser instead, so I can trap
All right. Okay, you don't have to dump them if you want to do something with them. There's plenty of time to get work done this weekend. So. Ooh, going. Okay. I think we're all set then, Crystal.
Okay.
Thanks so much. Yeah, she has a perfect name for them.
So what's the form of that? Is that a metal?
Yes, ytterbium is a metal when it's not atomic. When it forms when you get a solid chunk of it, it's a metal that conducts. Okay, so I just wanted to show you a few more slides, kind of sort of futuristic things. But not a whole heck of a lot. I think by now you saw that we can control these individual atoms. And in fact, the degree of freedom we store information is actually in the magnetism within an atom. I mentioned we have this outer electron. It's like a little bar magnet, and because it's an electron, it can only point in two ways: north up or south up. And so the nucleus of this atom also is a bar magnet, and so we have different configurations that have different energies. So when they're anti-aligned, we call that a 0. When they're aligned, we call that a 1. And we can store data in individual atoms this way. We can entangle atoms that way and so forth. There's something else we can do. This is a different laboratory across the street, across the hall from where Crystal was. Here we have two entirely separate chambers. It's a little hard to see that, but you might recognize a little bit of it. This tube that has a little microscope objective on the end, and the same over here. These two traps, they hold one atom each, and we were actually able to entangle them over this distance by having them emit photons. And the photons go behind this black, behind the black sheet, and something special happens with the photons that makes these two atoms entangled.
Photons are bundles of energy from all electromagnetic waves, correct?
That's right. They're the quantized version of light. They're like particles of light, if you will. And we use them in order to entangle these atoms. So these atoms were never close together, but they were each close to their photons. And then the photons sort of mediate the entanglement. So you can do this very indirectly. And the neat thing about having entanglement like this over a distance is we a few years ago in this lab, we did something called teleportation, which is, it sounds real fancy, but it's nothing more than communication. What we've done is taken a superposition, maybe 90-10, zeros and ones, any weighting you want, and we wanted to move that information. And the information means how much 0 and how much 1 is there. Is it 90-10? Is it 40-60? We want to move that from here to there without destroying it, so you can't look at it. And one way to do that is just to physically take that atom and move it, but we don't want to do that. Let's say that's not available to us. Because they were previously entangled, we can do that. And why we call that teleportation is that we've reconstituted the state of this atom over there. Now, remember I said we reconstituted the state of the atom. The atom is identical. It's the same ytterbium species, so you can't tell the difference. So we call it teleportation. I think that's a fine word for it. But in terms of teleporting big objects, you confront the same old problems. It's too big of a quantum system to think about encoding information that way. But I could say we teleport the atom from there to there, even though we didn't move any mass, we didn't move any single atom, we moved the information it contained. And that's all that matters. Quantum mechanics says all that matters is the information that's contained. The quantum state is all that matters. A ytterbium atom does not have a soul, as far as we know, so two ytterbium atoms are going to be exactly the same. They're not like people. The reason people are different is it's all our 2 to the 10 to the 27 interactions. We're all different. That's what a physicist would say. Yeah, the question back.
So how fast was that?
Oh, it was really slow.
Oh, okay.
It has to do with the photon connection is very inefficient. Come on in if you like. The photon connection is very inefficient. Now, there's no faster than light here either. You can never do it faster than light. We actually had the way we did this is we prepared a state here, we entangled them, and then we measured this state. We destroyed this atom state, but based on that measurement, we then did something over here. So we had to have regular old classical communication, like a telephone call from one to the other. You're always limited by the speed of light in this protocol, but it's a good way to move information around. In fact, it's the only way we know how to move quantum information around. We call it teleportation. Yeah.
Can you use entanglement to maybe somehow make a communication device over large distances?
Absolutely. There are ideas on how to communicate between many parties and do things that you couldn't do classically. I'm not a theorist in that area, but there are lots of ideas out there. None of them are clear-cutting killer applications at this point. But cryptography comes up again and again. The nice thing about quantum states, if somebody measures them, they get destroyed. And so that protects them from being measured. So there's a natural application for cryptography. If we send data using quantum bits, of course somebody can cut off your line. They can measure it and you never get the message across, but they can never read the message. So that's one big application.
So how do you physically get this state from one trace to the other? I mean, you say it's like a telephone pole.
Yeah, it's electrical, so the computers over here, the computers did something over here based on what they learned over there. We measured these photons, and that entangles them, and then we made a measurement using microwave. I mean, there's all kinds of stuff we do.
Right.
But the computers control all this, and they know what state the atom is in, 0 or 1. And given that information, we then do something over here. It's all prescribed. It's just a lookup table. If we measure one thing, we do this. If we measure another thing, we do something else. And then in the end, we verify that we had the initial state was good.
Would it be possible to put a quantum computer on the internet? Or hook it up to
You'd have to have a quantum internet. You'd have to be sending individual photons instead of classical communications. So when you think of teleportation, you of course think of these guys. And if you think about quantum mechanics for a little bit, remember a single quantum bit can be in 2 states at the same time. 2 quantum bits can be in how many states? 4 at the same time, right? 0, 0, 0, 1, 1, 0, and 1, 1. Every time you add a quantum bit, you double the size. If you had 3 of them, it's 8. So it's 2 to the n. It's exponents of 2. So if you have 10 to the 27 atoms, each of them say are only in 2 states, the possible configurations I can be in is 2 to the 10 to the 27. So this is a number that's so ridiculously huge we can't write it down. And you couldn't write down. There's too many zeros to fill the universe. So this is why you'll never teleport big things. There's way too much information. We can't deal with it.
Is it more than a Google Plus?
Way more. That's nothing compared to what we're talking about here. You just can't. I just can't even fathom a number that big. There's not room in the universe to store that number on all the particles in the universe. Okay. So I'm gonna start to wind down. Except to note that today's hardware is pretty exotic. You saw a picture of the laboratory. You didn't see the duct tape and epoxy, but it's not. It doesn't look like the inside of a computer. It's not. We need lots of engineering to help us there, but we're starting to work out all the dirty quantum physics of the individual devices. And we're sort of at the level as we were in classical computing a long time ago when we had these nasty vacuum tubes. This computer, there's a full-time guy who his job was simply to replace these vacuum tubes that would break so often. That's sort of like where we are now. So we have graduate students instead. But the future actually looks really bright. This is just last month's issue of Science magazine. This is one of our chips, actually. We're now trapping these ions, these atoms, on a silicon chip. This is a pretty big chip, though. It's about 1 inch by 1 inch. It's not a microprocessor. But these little piano keys, they're electrodes, and we can trap individual atoms above them And so engineering is happening. I mean, I didn't package this. I'm not a
Is
silicon
it kind of
expert.
semiconductor?
It is silicon. Silicon, this is all silicon, and it's doped silicon, so it can carry voltages. And as a plug for the JQI, the Joint Quantum Institute, my research is only one corner of it. We have pretty much anything that shows any type of quantum coherence, we have it at JQI, and we research and investigate that physical platform. There's lots of them, from individual photons, molecules. This is supposed to be a photon wave packet. This is a very funny so-called quantum dot. It's a defect in a semiconductor crystal. Some of the engineers here do that. This is a nitrogen. This is diamond that has a defect. They're superconducting circuits. These are atoms in so-called optical lattices. That's another hot field that we have some great expertise there. Anyway, so this is a plug for our JQI. It's a real neat place, very speculative. There's a good reason this stuff is not being done by Intel and Microsoft and Motorola right now. It's not ready. It's not ready for the marketplace. That's why it's at universities. I think many of us think that in 20 years it will be at these industrial concerns. So back to Tom Clancy, if you have to go to Tom Clancy. One reason I'm in this field is that the young people are coming to it in droves. It's very exciting. If they know anything about computers, they want to look 20 years down the line. When they're in their 40s and 50s, they want to be working on this stuff. And as Tom Clancy realizes, one of his heroes in this book, he actually gets it. He makes a big quantum computer, and he's asked, how did he do it if all the conventional tricks didn't work? You know, they're very small. And he says, because I'm smarter than they are. There's so many smart people out there that are not yet in this field, and they aren't coming to this field. So I'm actually very bullish on the idea that quantum computers will be general purpose machines in a few decades to come, as we try to harness so-called Schrodinger's cat, making bigger and bigger quantum superpositions. Maybe only a few hundred
at
atoms.
the same time as the Schrödinger paradox, correct?
I don't know that one. But the
There's a lot of
Schrodinger's cat is huge. It's 10 to the 26 or 27 particles. I don't think that'll ever happen. Nothing that big. Even if we did it with a few hundred particles, it would be very interesting and many problems to go on. And this, of course, we have something here already. This is from The Onion, one of my favorite newspapers. That they had, I guess the company Hager has a new line of quantum slacks. And I will end, this is my last slide, returning to Feynman. Look, the rules of quantum mechanics are weird. You have to get over it. That's what they are. That's it. We can use it. And it's interesting what Feynman said about quantum mechanics. He was one of the skeptics that there was anything interesting about thinking about this problem, but listen to what he says here. We've always had a great deal of difficulty in understanding the worldview that quantum mechanics represents. This idea that a measurement destroys the system. The act of looking at something changes it. Okay, I still get nervous with it. It's not yet become obvious to me that there's no real problem. I cannot define the real problem, therefore I suspect there's no real problem, but I'm not sure there's no real problem.
Yeah.
This guy's really smart. Einstein is really smart, and they both failed to really nail it all together. So I think it's something certainly in my lifetime we'll live with. Maybe somebody super smart will come and show that in fact there's a more complete theory that describes this. In any case, it doesn't matter. There will be quantum engineering. We will have these quantum computers at some time. Whether or not you like the laws of physics, they will exist. So with that,
Still trying to find the GTU, the grand unification theory.
Oh man, I don't know about that. That's what Einstein really wanted to look at. But anyway. So thanks for your attention, and I'll entertain any questions.